Alright, this time I'll talk about the problem sweet butter. So in this problem, we will search through each of the possible nodes and see if that one has the shortest path or not. And we can do this because there are only 800 nodes at most and only 1450 edges at most. So here is my code. First, we're reading the position of the cow. This array will store where each cow is at. And then here we're reading each pass. So these two, U and V, are the two different pastures, and L is the length between these two. So we will use an adjacency list to keep track of all the possible paths. The first part just will keep track that there's a path from U to V and it has a length of L. And this one states that there's a path from V to U and it has a length of L. We do both of this because this is an undirected path, so the cow can go in any directions. And then here we will test out each pasture as the source. So this basically is where we'll put the sugar of at. So if, for example, we will start at checking if the sugar was at pasture 1, then what would the total number of steps take all the way to if the sugar was at pasture P. So here we'll use BFS. This is a different version of BFS, a bit more complicated than the normal one, because this time we're counting the weighted edges. So we cannot just add 1 every time. We have to consider the distance between each node. So here, instead of using a queue, we will use a priority queue. So a priority queue will keep track of all the things in a sorted order. And originally, if you just create a normal priority queue, it will first put the biggest value at the front. But here we want the shortest path, which is the smallest value, so we should put this in a reverse order, and this is what this part does. So here I use this type diff because to define that this pair int is just PII, because if I don't do that, then this line will look too long and complicated. So normally a priority queue will just have this one statement here, but if you want it in the reverse order, you will have to add this. So first, this is the same thing as a normal BFS. So this is a pair. The first part is the distance of this current node, and this one is where we are currently at. So first we will start at the source, and we didn't make any moves, so this distance will be 0, and also we will use a distance array here to keep track of the actual distance. This is our current distance that we're testing out. So while this is not empty, this means we still have a path to search. We will assign these two numbers to our front of the queue. So this will give us the current node with the shortest path. S will store the path, the number of steps taken, and U will store this current node. And we already have these values, so we can pop this front one. And then we have to check, because when we use this loop afterward here, we might update the current distance, and we could have found a more efficient way already. But this pair was already stored in the queue. So now, if we've already found a better solution, we don't need this anymore. So we can just continue. We can just pop this and continue. We don't need to do everything after here. And now, if this current distance is smaller than the distance to U, then we can do the following. So this auto E will check all the edges that you have, and we will assign the two values from each of these pair. See, because these are pairs, remember here we have a node and a length. So these two will, this will be the destination, and this will be the length of this. And now we need to check this. So basically we have to check if the distance to our destination is greater than the current distance plus the distance from this edge. So if this edge is actually takes less time than the current distance, then we will set our current distance to this s plus the d, and also we will push this into our priority queue. So the next time we can go through this node and check for another more efficient distance or something. So this will keep on going until we found all the efficient distance, and this queue will finally be empty because all of the distance will be already found. Here we will just use this loop to go through each of the cow to see where they're at and add their distance. So here I'll first check if the distance to pasture I is equal to infinite. So here I define infinite as this. This is just a number that can be assigned using this memset. Because if you just do int max, you might get overflows, and also you cannot use this function to just set everything inside this distance array to this number. So here we'll check if this is infinite, then that means we haven't found the path. So we can just return infinite, meaning that there isn't a way if we start at the source, but I think it's possible to reach everything. But I put this here just in case we have any extra cases. And otherwise, if this is not infinite, this means we already have a distance. So we just increase our total number of distance traveled by this distance to pasture I, and finally we'll return this total count. And here we'll go through this every time from 1 to p, and every time we have this, we will compare our answer with this. If the answer that we just got is smaller than the answer that we currently have, we will set our current answer to the smaller one. And then at the end, you just have to print this out, and you're done for this.